example of SL2 at admissible level. Now, the study of the representation theory, I always think about it as being divided into two parts. First, understand the abelian structure, and then understand the Moidal structure. And the last talk here is telling you what I can say about Moidal structures. Now, basically the axiom of rational conformal field theory translate to the statement that the category of a rational vertex algebra, so not what I'm discussing here, should be a modular tensor category. And it has, and this is something that Huang Iji has celebrated for. Now one wants to extend all that to the non-zero setting, and a theory of tensor categories of vertex algebras has been developed by this Rutgers group. And it basically says that if certain assumptions on a category of modules of a vertex algebra are satisfied, then intertwining operators can be used to define a tensor category structure. This is then automatically always a braided tensor category. And what is the difficult thing in the theory? The difficult thing is to verify that the thing that you want to be the tensor product is associative, because you have to analytically continue intertwining operators for that. And how can you guarantee that you have this analytic continuation? You can guarantee this if you have good differential equations for correlation functions. And there is one finiteness condition that guarantees the existence of differential equations. And then also it allows you to show that your tensor product is indeed associative up to natural transformation. And this finiteness condition is nothing but a technical algebraic condition. It has the advantage that it means that if you want to verify that you have a tensor category, you can stay purely algebraic. You only have to think about which modules satisfy this finiteness condition. So this condition is called the C1 cofiniteness. It has a good news and a bad news. The bad news is that it doesn't apply to too many modules. The good news is it's something that is very well tailored to superalgebras, because odd elements of a superalgebra have a tendency to square to zero, and nilpotent elements make it much easier for modules to be C1 cofinite. So in some sense, one should take this as the tensor theory, or as the state of the art is really tailored to be very good for superalgebras. So here is the definition. It is just you take a module, and then the subspace that is spanned by the action of all -1 modes is called the C1 subspace. And so you can take the quotient as vector spaces. That's a certain dimension. It's called the C1 codimension. And the module is called C1 cofinite. If it's codimension, it's finite. Very natural definition. Now, and the C1 cofiniteness, I think, has a few good properties. If you have an intertwining operator from M1 times M2 to a third module M3 that is surjective, then M3 needs to be C1 cofinite if M1 and M2 are. So this means the category of C1 cofinite module closes under the action of intertwining operators.
What is to be surjective? What is to be surjective for the intertwining?
So it's a surjective. That means the image is M3.
In the image is what you can do from
the
operations.
Yeah,
take the modes of this.
Yeah, exactly. So this means you take elements in M1 and M2, right? The intertwining operator is associated to M1. It acts on M2. It gives you a formal power series with coefficients of M3, and the coefficients that appear here, they span M3. That's what it's meant. Most importantly, it guarantees what I said in the last slide. It guarantees that associative, the tensor product is indeed associative. And then one has played a game, namely one has tried to formulate theorems that say, assume we have a category of C1 cofinite modules of a vertex algebra, then we have to add a few conditions so that they guarantee existence of tensor category. And example for example that has been studied, conditions have been removed, and last Friday, so it's kind of nice, very recent, EG removed every condition. So it has one big caveat. A quotient of a C1 cofinite module is always C1 cofinite. A kernel does not need to be. This means that we get a tensor category, monoidal category, that is not necessarily abelian. Needs not be closed under kernels. This is quite annoying. It is what it is. And in practice, it means what you know really want to show is actually that categories of C1 cofinite modules are closed under kernels. It should most often hold, but it won't always hold.
Last Friday, an example appeared. What happened last Friday? An example appeared.
Oh, the paper on the archive appeared. It's really, I mean, this statement, we knew that it should be true, and since the theory has been developed by EG, he's the best person to verify that it's true, and luckily he did it. And he put it on the archive last Friday. Now the big problem is I was always restricting here in these lectures to the case of SL2, and if you remember a while ago, I wrote 4 categories: category of weight modules. Right, that's the most general category. It contains the lift of any SL2 module, affine SL2 module, and then any spectral flow twist of it, and also more modules. Then one had this subcategory of lower bounded modules. These are the category that comes naturally from finite dimensional SL2 modules. This has the subcategory that is associated to highest weight modules, and then one has the subcategory that is associated to finite dimensional SL2 modules. That's what's called the customalistic category. Now the problem is for a module of an affine vertex algebra, the C1 quotient can be naturally identified with the top space. So it means it has the same codimension as the finite dimensional SL2 module it comes from, the SL2 module that it comes from. So it's finite if it comes from a finite dimensional module. So that means a module of the affine vertex algebra C1 cofinite if it comes from finite dimensional SL2 module. That's unfortunately a super small category. If you remember my classification, the classification I presented, almost no object is in the subcategory. So this is a big problem because, and you need a creative solution. This solution is called Kasama-Suzuki duality, and its vast generalizations. We presented that, right? And so Shigenori presented this duality and part of its vast generalizations. So it's kind of good. And broadly speaking, it's a very good correspondence between certain families of vertex algebras, usually W algebras, and certain vertex superalgebras, usually W superalgebras. And good realization means you have a good functor between them that ideally you can upgrade to ideally you can upgrade to a tensor already. And for SL2, it turns out is the dual, is the n equals 2 super Virasoro algebra in this Kasama-Suzuki duality. So Kasama and Suzuki are ancient string theorists and string theories of the first phase. And that was one of their most important examples to construct sigma models that were used for string theory. So the n equals 2 superconformal algebra is the W algebra of the superalgebra SL2/1, the principal one. It has 4 generators, 2 odd ones of conformal mate 3/2, 2 even ones, the Virasoro field and the Heisenberg field. These are the OPEs. The details are not so important.
Sorry, is there an obstruction to the existence of products outside of the C1 cofinite setting, or it's just HLZ convergence issues are not kind of resolved?
Can you say it again?
So outside of the C1 cofinite setting, is there an obstruction to the existence of the product, or there's just problems with convergence in terms of like this HLZ?
Yes, so the convergence is there. I mean, another obstruction is the existence of a universal intertwiner. For example, in we consider last lecture, there the point is the fusion product is really an integral of modules. So that means it's an object and a completion. And working with completions makes life substantially harder, of course. And C1 cofinite guarantees that you don't have to work with completions in this setting. So it's absolutely actually a very interesting thing to lift everything to examples as Jörg has presented. And but from my point of view, that is out of reach. So what you do is you now want to go from SL2 to Super-Virasoro and back. Well, SL2 is generated by E, F, and H. H is a Heisenberg field, it's already good. Good, E and F have conformal weight 1, and they have a Heisenberg weight plus or minus 1, or depending on normalization, right? So what one does is one simply adds two free fermions. One calls them BC goes, they have conformal weight 1/2. And so if I take the normal order product of a B with an E, it has conformal weight 1 plus 1/2 and the spot. So that means it has the same parity and the same conformal weight as the G plus minus that under OPE generate in this two superconformal algebra. And so one can simply compute the OPE of the fields constructed in this way, and one observes this is not a half computation, that they have the same OPE algebra as the n equals 2 superconformal algebra. And that's actually the essence of Kasama-Suzuki duality in this case. But you also want to go back, and for this we simply notice the first boson fermion correspondence is simply saying that two free fermions are the same thing as the vertex algebra of the lattice integers. So in order to go back, I stay with the integers. I just change the signature of my form. This means I rescale the lattice with the square root of -1, so that the norms are changed by a minus. And now I take this the Super-Virasoro algebra. I denote it here SK so that I don't have this long symbol. And now I do the analogous thing. I just, instead of tensoring with the lattice VOA of the integers, I tensor it with the lattice here of minus square root of -1 the integers. Why do I do this? Because this lattice view is generated by fields that are analog to the fermions. I call this, I call them E plus -1, but they are also odd, but they have conformal weight -1/2, not +1/2. That means if I if I multiply a G plus with an E to the Y, the parity changes, the conformal weight decreases by 1/2. So in this way, I get fields of conformal weight 1, which I call E and F. And again, it's nothing but a simple OPE computation that this inverts this construction in the sense that this E and F give you the affine vertex algebra of SL2. So you see, I mean, of course, Super-Virasoro and affine SL2, they are not isomorphic; they are very different VOAs. But you can go from one of them to the other one in a very straightforward way. Okay. Precisely saying, the way one could say this is, if you take the affine vertex algebra and you tensor it with the Heisenberg, you get a conformal embedding in the Super-Virasoro times one of the lattice VOA, and the same thing the other way around. More precisely, you can formulate this in terms of relative significant Lie algebra cohomologies to get good functions, but that's technical, and that was Shigenori's talk. The point is, this is what Shigenori talked about, is that if you formulate this problem correctly, then you get blockwise equivalences of abelian category. So we do know SL2 at admissible level, so without any work, we also know the category of modules of the
So what means blockwise? What means blockwise?
Blockwise, it has a block decomposition, right? So that the different blocks don't have any extensions.
If you have an equivalence of categories, if you have an equivalence of categories, blocks will be equivalent to them.
It's not an equivalence of categories. It's only blockwise equivalence. It's weaker than an equivalence of categories. It's not an equivalence of categories, but you should think about it as an almost equivalence in the sense that it's almost abelian equivalent because there's a blockwise equivalence. And so you have it's a technicality. and it is also a correspondence in such a way that one of them has a monoidal structure. It induces a monoidal structure on the other one. The lattice VOA twisted, that's the point. And in particular, if one of them has a tensor structure, the other one has. It's also, if you know the fusion rules of one of them, you know the one of the other one. It's a very good correspondence. It's just not an equivalence.
Excuse me. Why have this correspondence monoidal structures? Because they have different blocks. Right? Not a blockwise equivalent.
Yeah.
Monoidal structure will mix the blocks.
Yeah, absolutely.
But you don't have equivalence of categories. It's just one has more blocks than the other, right? Same type.
It's more you have a whole family of functors. And each functor, depending on which block you choose, is either 0 or gives you a block on the other side. And depending on which functor you apply to which block, you get accordingly a block on the other side. So it's just a little bit technical. Yeah. But really the point is here you see this. You see super Virasoro is a conformal extension of SL2 times the Heisenberg. And so the tensor category structure on SL2 times Heisenberg inherits a tensor category on the larger structure and vice versa. This is really here the point. So this whole Kasama-Suzuki duality is a story in its own right, which she talked about a little bit. Now the point is that the super Virasoro side is so nice because you see SL2 is generated by E, F, and H, and so and because E and F they are not nilpotent, the C1 cofiniteness is a very subtle thing. On the super Virasoro side, they are replaced, morally speaking, by G plus and G minus, each of them squaring to 0. So the problem of showing the C1 cofiniteness is much more promising. It's nonetheless actually a really technical computation to verify it, but it can be done. And it turns out every module, in this case, is C1 cofinite. So the complete category of weight modules of the super Virasoro algebra satisfies the conditions of one Minkowski junk. And then via this Kasama-Suzuki duality, luckily, the same thing is true for SL2.
Kind of intuit what happens. So I think earlier you told us that this thing, the modular is not C1 cofinite, so that you can't have a product, and then
No, I didn't say they can't. I just say the conditions of the theory don't apply directly.
Okay.
All right. So the problem is you have to. The problem is you have to guarantee this convergence of the correlation functions, which for which one has one condition that ensures that. But now I'm saying there's one more condition that ensures it, namely if you have a good duality that transports tensor category structure, and you can show the convergence on the other side, then you're also good. Yeah.
And the super came from, I think this was like clear from what you said, but
yeah, the super comes really, if you see it here, because you take SL2 times 3 fermions, right? And so there you go. The 3 fermions are trivially super. Now, really the interesting thing is that this whole Kasama-Suzuki duality generalizes vastly, which is a whole other topic. So that this approach is actually a promising approach. It's not something that you should think about being restricted to SL2. Okay, and now the very interesting thing is that if you have a tensor category, if you know that you have it, then you can prove a lot by doing almost no VOA theory. It's kind of nice. So now and we have had a few talks about braided tensor categories, for example, by Martin yesterday, in particular about commutative algebras, Chelsea gate lectures, and you know, all you said is kind of useful. You will see bits and pieces again here.
Thomas,
Yeah.
I get the feedback from the audience that you should speak up.
Okay. So now I want to explain how to give structural results about the representation category of SL2 using this free field realization that we have used previously to simply study the abelian category. So recall, especially in the last lecture, I have presented this conformal embedding of SL2 in the Virasoro minimal model times this half lattice VOA, and we have used this to actually classify our weight models of SL2. And now I will use the very same thing to prove structural results about the tensor category of weight models of SL2. So this means we have here, in general, the following setup. We have a VOA that we are interested in, V. V is our SL2 at admissible level. We have a larger structure, A, in which V embeds conformally. A is our rational Virasoro algebra times this half lattice VOA. With representation category is semi-simple. With representation category we understand very well. And now we want to ask the question, how much is the category of V modules that we will here always denote by U is determined by the category of A modules that in this slide is denoted by C. And the idea is that the answer is almost completely if certain very technical conditions are satisfied that seem to be kind of built in good realizations of VOAs. So I want to formalize it, and so this is exactly what Martin talked about last lecture. So we have a braided tensor category, and so now one can ask about algebras in the category, right? An algebra has to have a multiplication, so an algebra in the tensor category has to have a multiplication. That means a map from A to A to A. You want this algebra to be unitary. You want to have an embedding of the tensor identity in it, and you want this multiplication to be associative. Associative means it doesn't matter whether you first multiply on the first factor and then on the second, or vice versa. And if the category is braided, you can also ask whether this algebra is commutative. Commutative means the multiplication commutes with the braiding. Right? I can take A times A, I can use the braiding to swap the factors and then multiply the algebra as commutative. This has no effect. Now in this setting, if one starts with a category U, and this category U, we always want to think about our category of weight models of SL2. One has the notion of a tensor category of A modules in U. One is this category is a tensor category, but not necessarily braided. But it has a subcategory of local modules. This is all very well studied in the category literature, which is braided. And this is called the subcategory of local modules. Now, if we have this this relation, one has two obvious functors. So an object, an A module, what can it be? It must be an object in the underlying category together with a multiplication morphism. In particular, you will always have a forgetful functor where you do nothing else but forgetting the multiplication. Conversely, if you have an object in the category U, you can lift it to a module by simply tensoring it with your algebra and use the algebra multiplication to define a multiplication of the lift. So these are two functors. Restriction is not monoidal, but induction is monoidal. That's extremely useful. And the two are adjoints to each other. So these are kind of the useful properties. And with this setup, one can now start to do a lot. Okay. And it starts, in fact, it starts with an article. It starts with articles by Kirillov, Creutzig, and also by Christoph, Ingo, Jürgen, and Fröhlich a long time ago, who maybe 20 years ago, who were maybe the first influence on this, and it was only formalized 10 years after that by Creutzig. And they noticed that in our setup, what I call the free field algebra, is the same thing as a commutative algebra in the tensor category. And what we did here, Robert is here, we lifted the statement also to the category of local modules, that we showed that the category of local modules is braided tensor equivalent to the category of modules of the free field vertex algebra. So in particular, this means if you have a small VOA and you want to study the representation theory of a bigger one, this is purely the problem of studying the category of this local A modulus. This is something that is kind of relatively straightforward. Of course, going back is a very, very subtle question, and usually the category of local modules does not have too much information about going back. But in our setup, it has, and this is really nice. And this is in particular extremely useful to show many structural results about representation theory of, for example, SL2 at admissible level. And in particular, from my side, really the moment someone understands the abelian category of a vertex algebra good enough together with a suitable free field realization, all I have to do is I have to study the category as such. I don't have to work with too many vertex algebraic techniques anymore. In particular, in this setup, it started really with the work of my PhD student, Matt Rupert and Simon Lentner. So Simon explained to me what Nichols algebras are and how one constructs quantum groups out of Nichols algebras. And Simon also has given a talk about this last week. And what we did is we translated the quantum group language to this setup where you have a good realization of the vertex algebra. And we observed that, morally speaking, the quantum group realization in a certain way is exactly what the free field realization does in some way. And then we kind of noticed that effectively we actually found a setup to also prove other interesting structures like fusion rules, rigidity of ribbon structure of the category, and things. So really the first article here is the key insight in many respects. And it's a bit funny because one has very for tensor category people, very unusual properties. So the key property seems to be that this commutative algebra, this big VOA, is a single indecomposable object for the smaller VOA. But usually you are used to big direct sums of objects. Here it's a single indecomposable object. And this should translate to that you only have logarithmically twisted modules. Only having logarithmically twisted modules, you should understand as the statement that every module of this algebra A that is irreducible already needs to be a module of the vertex algebra, already needs to be low. So if you take a generic commutative algebra, this condition will never hold. And then there's another relation that simple local modules and simple modules of the smaller VOA have to be in one-to-one correspondence. All these three properties seem to be super closely related. In particular, usually one knows the third property. Proving the second property is relatively easy, and then one uses these two to prove property number one. And it seems that if one has these three properties, then you have to only find some additional but relatively mild conditions, I would say, to get all this other interesting structure. So it's really, so if you're working on tensor categories, what you should take out of that in this framework, we are interested in non-semi-simple categories where we have commutative algebras that are a single indecomposable object, and then having this additional. Then we have a rich theory. So somehow, this is a key slide because these properties are very unusual. For if I asked Chelsea, you would probably tell me this looks strange, right?
Yeah, it's very particular.
It's very particular, and only under these particular properties you can prove.
But the extensions are different. So there are the extensions of simple objects, of simple modules, which are not local.
Yeah, exactly. But you have many extensions. It's just, and they are not local. It's just that every simple composition factor is local.
Did you say that A is the only simple object in local modules?
No, not at all. Not at all. Not at all.
How many are there?
Yeah. Okay.
But Thomas, is it really so strange? Because if you think about the W2-3 algebra, It is not simple as a module over itself, but it is still indecomposable. So I think you are perfectly within the reasonable scheme.
I also think I'm perfectly reasonable. It's just that, yeah, thank you. If you look at the literature of people having studied commutative algebras, then you will rarely find, you won't find too often such an example. I think this is what I wanted to say. And what I really want to do is I want to point out these are the key properties for this setup.
Except, of course, for commutative algebras in fact, which have been studied by certain Fractional.
Some people.
What so for example, it's always a good idea to work with other people. And so Kenichi Mitsu and Harshit Yadav, they had worked on, have a nice paper on exactness properties of commutative algebras. And Harshit was our postdoc in Edmonton at that time. And so we got to talk and I explained to him this our rigidity issue. And then together with Rawat and the experience of how the setup that I presented in the last slide is useful for quantum group correspondences, we were able to derive a theorem that tells us that we have rigidity, so that we have a ribbon structure. This is kind of that we have duality, which was asked in the last talk. So what do we need to know? We of course need to know that we start with a vertex algebra that has a tensor category structure, and we want it to be locally finite. So that means every object has finite length here. We also want a technical condition that the vertex algebra is its own contrarian dual. Now we want to know that the bigger VOA already has a rigid category of modules, and then we are asking under what conditions is this rigidity gets inherited to the category of modules of the smaller VOA. And the point is that the key condition is here the third condition, which I also listed in my key properties, namely that every A module that is irreducible is already local. So this, and why is that so interesting? Because the vertex algebra is not necessarily a ribbon category, but it always has the structure of a Grothendieck category, and itself its own contrarian dual, it's an R category. So this is something that, for example, Christoph and collaborators have first studied. And we are now able to show that if you have rigidity, and then you can use this R category structure to do an induction for the length to prove that the whole category UA is already rigid. And then there's a relative center construction that allows you to show that U is rigid. So you show, the point is, the point you should take here, if you have this nice property of that every irreducible module is local, then under some additional relatively mild condition, then U is rigid. So really the only additional key condition is that, of course, the induction parameter has respect for two duality structures. That means the induction of a dual object is the dual of an induced object.
So our category is Grothendieck Verdier.
Grothendieck with the identity being the dualizing object. Yeah.
Induction is a monoidal functor, right?
It's always a monoidal factor.
So you should preserve those.
Hmm?
You should preserve those as a monoidal functor.
It should preserve.
Just the ordinary rigid structure is.
So this is not guaranteed in the setup that it preserves those. I mean, so the point is that the category U we start with as rigid is an enormously difficult question. Right, so we only start with an R category, and
It's not indicative.
yeah.
Well, so your compatibility is what really? What are these two dualities?
So the R category structure on U and the rigidity structure on UA.
UA.
Mm-hmm. But we use the R category structure to prove rigidity on UA first. And the point is, if you have this setup, you will always have a functor from your category U to the you have a functor from your category U to the Drinfeld center of UA.
Yes.
And what you have to show is that this functor is fully faithful, and because if UA is rigid, the Drinfeld center is rigid, and if it's fully faithful, if you have a subcategory, and if the subcategory is closed under duality, then it's a rigid subcategory.
And it is fully faithful in very general setup.
Again, that is a very subtle question, because tensor product is not necessarily left exact. And if it's not left exact, then fully faithful is not an obvious question. Oh, and these are not general things because we have very few structure to start with. And we cannot assume we have an exact tensor product. We cannot assume rigidity. That makes vertex tensor category studies so hard, because you first have to show that you have this good structure. Of course, now that we have rigidity, we also have exactness of tensor product. You kind of have to prove elementary properties in order to prove good properties afterwards. And so in particular, verifying these conditions is what we did. And so the category of weight modules has indeed honest duality. And a ribbon twist is built in. The next thing you get inherited is the Berlin's formula. And it basically follows from the same setup. So I thought maybe I'd put in 3-4 slides on the original Berlin formula. So we start with a tensor category. We have its Grothendieck ring, and then we can define the Grothendieck fusion rules via this formula, where the fusion coefficients are the multiplicities with which the Z appears in the tensor product of X times Y. So if it's semi-simple, it is just the multiplicity with which Z appears in the fusion product. And well, in conformal field theory, one calls these numbers the fusion rules. And for obvious reasons, they are very interesting. And usually they are not easy at all to compute. Now, on the categorical side, on the other hand, if we start with a modular tensor category, so a finite semi-simple category where the Hopf link, that means that is given by the trace of the double braiding, is non-degenerate. In that setting, computing these fusion rules is the same thing as knowing what these Hopf links are. And so first of all, what you do is here, you don't look at the closed Hopf links, but an open Hopf link. So I take a double braiding of 2 modules and I close it only at 1 strand. And then, because braiding is natural, composing 2 open Hopf links is the same thing as taking the open Hopf link of the tensor product. And because that, and so that means for open Hopf links, one has kind of the nice identity that the composition of 2 open Hopf links is the same thing as the sum of the open Hopf links corresponding to the tensor product. Now this is interesting because if I have this identity, I can close it on both sides. And if I close it on both sides, one takes the trace. Closing means you get the closed Hopf links, these S's, and the identity that I wrote down graphically on the previous slide in terms of closed Hopf links is the identity here. A modular tensor category, this S is an invertible matrix, so you can invert and you get a closed formula for the fusion coefficients. So, and this is what it means that knowing the Hopf links is the same thing as knowing the fusion rules in the modular tensor category. And now the Berlin formula is the statement that for a rational vertex algebra, you know what the closed Hopf links are. And so that means via this formula, you know what the fusion coefficients are. Now, what you should remember is that the fusion coefficients are an expression of type sum S times S times S inverse over S. Labels are something. Because in a rational vertex algebra, you can write down what the graded character is. So that means it has weight spaces. The graded character is the sum over the dimension of the graded components, weighted q to the n. And you think about as q being e to the 2 pi I tau on the upper half plane. On the upper half plane, the modular group SL to Z X via Möbius transformations. And the deep results of rational VOA theory is that these characters form a vector valued modular form under this Möbius transformation, and moreover that the S matrix that you get in this way, which is called the modular S matrix, is the same as the categorical. And somehow this is a very efficient game in a rational vertex algebra because characters are relatively easy to compute, modular transformations are relatively easy to compute, evaluating sums are relatively easy to compute. So you could say in a rational VOA, this is simply a relative efficient framework to get this fusion. It's also a natural consistency condition because if you follow the axioms of rational CFT, a la Moore and Seiberg, then one of the first consequences of these axioms is that this Valinde formula is true and is given by the modular S matrix. And so that means you should think about it not only as being a useful formula, but also a useful consistency check that you're on the right track. Okay. Now we are interested in cases like SL2, but SL2 has a problem that it's neither semi-simple nor finite. Not finite is a priori not such a big problem because it just means you replace sum by an integral. But what the problem is that not every module is has a nice modular transformation. And I presented that at the end of last talk where I have shown you the theorem with redoubt, where was given a nice modular transformation formula for all modules that are also modules of the free field algebra, but for all other modules one had to use resolutions, something quite complicated. And this is also why one likes to call this the resolved Valinde formula after all. Now the key property that makes this resolved Valinde formula work is this, this slide. So the key reason for the Valinde formula to work is, first of all, this induction functor is a monoidal functor, and that can be translated to the following statement. You take your bigger VOA A, you induce it, so you view it as a module in the smaller category, you induce it as an object. This is just A times A, and now you try to compute this, because the statement is if you take two modules of your free field algebra, M1 and M2, then the tensor product of these two modules with this induction of A to an A module is the same thing as the tensor product of these two free field modules M1 and M2 viewed as modules for the smaller VOA. So this is a relative direct consequence of induction being monoidal, but it is an extremely useful property because think about it is the following. Forget about the forgetful functor here. And say tells you the tensor product in the category we are interested in is the same thing as the tensor product in the category that we know. If we multiply the tensor product, if we take an additional tensor product with an instructive object that we call n wants to stand for nilpotent or Nichols. And then and the other key thing one has to prove is that the S kernel associated to this distinguished object coincides with the inverse of the S kernel of the V. These two properties, these two observations essentially imply the resolved Valinde formula. And I should also say that this property is essentially a consequence of this property if you follow it through very, very carefully. So that's a longer argument. Now, to recall this in our example, one had to replace these atypical modules by resolutions in terms of typical modules, and they give rise to long expressions. But if you regularize carefully, then they can be summarized in nice rational functions. And in particular here in this nice rational function, you see if you take the inverse, it's actually a polynomial and roots of unity. So in fact, you can even read off from that expression what n should be. So in our example, what we mean now by the resolved Valinde formula is we take the same thing as in the rational case, just that we replace the sum over all modules by an integral over all modules, and we replace the Valinde the kernel is again this expression of type S times S inverse over the S associated to the vacuum. Just that it's here now, so it's the same type of expression. The only difference is in this expression that a sum is replaced by an integral, and so it looks a little bit clumsy. Now the Valinde theorem is extremely similar to the rigidity theorem. And namely, it says that if I can satisfy certain assumptions, then the Valinde formula of the VOA that we do already know inherits, gives a Valinde formula also to the VOA of interest. So in our example, our A was the Virasoro algebra, rational VOA, for which we know a nice Valinde formula, times this half lattice VOA pi, which should essentially think about it as a variant of a free boson. In particular, it has a very obvious continuum Valinde formula. This is really not a problem. So that means we have a setup where we have a larger structure that has a Valinde formula. And now the question is whether it gives it also to the smaller one. And the statement is, and you have to have some technical condition. But again, the essential thing is you need that the irreducible A modules are all modules of the free field VOA, and you need that there's a one-to-one correspondence between simple modules of your smaller VOA and your bigger VOA. If you have these two properties, and then also you have to assume that V can be, the vertex algebra itself can be resolved, can be written as a long exact sequence, where every term in this long exact sequence is a local module, and this resolution satisfies a certain technical grading condition that ensures that quantities at the end converge. So of course you will have a convergence issue, you have to guarantee it somehow, and the only way I could find this is by a technical grading condition. And then under also, this is really a very weak condition, this resolved Valinde formula holds. So to give it an example, if you take this for SL2, what you have is the answer of this Valinde formula computation gives you, for example, these types of fusion rules for two typical modules. And you see these n vir are the usual Virasoro fusion rule coefficients. There are some shifts by a label by plus at -1 here, and yeah, it's of this form, and this form. So in particular, it has 4 types of summons, which you can kind of see here in this expression, because the denominator is really a sum of 2 roots of unity here. Each one of them will give rise to one type of summand here. Okay. And now I want to so I want to say one more thing to this. All these things actually started with Simon, and what one always wants to do is see there are many natural sources of rigid tensor categories, but 2 very natural ones are categories of vertex algebra modules and categories of quantum groups. And it has always been a good guiding principle to relate categories of vertex algebras to categories of quantum groups modules. And this always remains under the name Kashdan-Lusztig correspondence, for the reason that Kashdan and Lusztig proved the first type of such an equivalence here as well. Now, if you know SL2/1 well, then you, in my previous formula, you would actually have, there one sees actually already an SL2/1 structure in there. And here, it turns out that for SL2, one gets an actual correspondence to quantum SL2/1, but one has to introduce a new quotienting operation, which we call partial semi-simplification. So semi-simplification is a well-known thing. So if you have a non-semi-simple category, then you have negligible morphisms that can't be measured by a trace. And if your quotient by the category that comes from these negligible morphisms, you'll always obtain a semi-simple category. Now here, what we do is we do this partially in the sense that we, morally speaking, we only quotient by morphisms that are negligible for the underlying quantum SL2 inside quantum SL2/1. And that can be formalized, which is a whole technical story, but it's closely related to what Simon presented in the last talk.
So this is not just like annihilating the Steinberg on the Steinberg tensor or anybody?
Yeah, so let me tell you what the partial semi-simplification of quantum SL2/1 is. How do you construct a quantum group? Usually you fix a Cartan, you fix a Borel, and then you have a positive Borel and you have a negative Borel, and you glue them together. You can formalize this in the language of Jeter-Drinfeld modules, and that's a very good language. And so then in that language, it says the quantum group of G is the same thing as the category of Jeter-Drinfeld modules for your positive Borel inside the category of modules for your Cartan. But you could either equally well do this parabolic. So for example, for SL2/1, the even subalgebra is GL2. And so you can then you can think about the positive odd part of SL2/1 as the positive Borel parabolically. And you can construct the quantum group of SL2/1 as Jeter-Drinfeld modules of the quantum group of GL2 with respect to the Nichols algebra given by the odd positive part. Under partial semi-simplification, it's now meant that you quotient by that you don't take quantum GL2, but it's semi-simplification. And so morally speaking, what you do is you quotient by all morphisms in SL2/1 that are negligible as morphisms for the quantum GL2. That's why we call it partial. And it seems this is simply something you can do, but it seems to be the thing that gives rise to VOA category modules.
This is big or unrolled or?
It's unrolled. Good. And then I want to mention one work I didn't mention, because much of this was done in a completely different way by these people, more in terms of really VOA techniques. So what I wanted to present here is that much of interesting structural results can be done if one knows how to use this language of commutative algebras and tensor categories quite well. Right, so. Okay, perfect. Then thank you very much for your attention.
Thank you very much for these nice lectures. We have time for questions. Can I ask you speculative questions? You were mentioning resolutions at several times. They have been quite important. So what is the perspective of the field of vertex algebras to develop in the direction of homological algebra, in your opinion?
Yeah, it's one of these neglected direction, a little bit like also this Leo will think is a neglected direction. I don't have good feeling, but I have the feeling that this correspondence between free field category and interesting category can be much more elegantly phrased in a derived setting, because really what you do is you start with the category of VOA modules of interest, then you have a larger VOA that whose representation category is semi-simple, and now you kind of would like to look at the variant of a category of chain complexes there in some sense. And you would like to say that this is actually equivalent to that would be my speculation, that in some sense you can do that.
How would this fit to the comment on one of your first slides about the non-existence of kernels?
the non-existence of kernel is that comment is that the theory doesn't guarantee the existence of kernel, but in practice you always want to prove in the end that kernels exist. So that's a technicality. It's a very, very annoying technical problem that we a priori don't know the existence, but eventually.
But it's a technical problem that comes from the prejudice that you want to work with abelian categories, right?
Yeah, in particular, it wants to say one thing. Ideally, we would like to get statements that don't require abelian.
Yeah.
And for example, Robert and I are discussing, because we have a very nice, very important statement somehow that vertex tensor category extends to completions, to limit completions. But for that, abelian is needed. And it would be really nice if one can remove the word abelian.
Just complete or co-complete or something like that. Just maybe complete or co-complete or something like that, because that's like the setting of Creutzig's work with local modules. Yeah, they don't assume abelian in that work.
Yeah, can I explain to you the problem, and then maybe you can say so, because it's a very interesting problem, but a bit technical. Yeah.
So you do this resolution, you're not resolving by projectives, right?
No, exactly. We are resolving by what you should think about as standard modules.
Yeah, okay, so there's like some high weight structure that I should think there.
So, exactly. Really.
I mean, is there an actual highest weight structure? Is there actually a highest weight structure? There's something like a highest weight structure.
It's just so they behave like highest weight categories.
Yeah.
But the standard models are not highest weight. For example, you also observe a nice BGG reciprocity, as you know from highest weight theory, but it doesn't come from. I guess on the quantum group side, it translates to the usual highest weight. On the quantum supergroup side. Yeah, that.
Is the tensor unit always simple in your examples? Like for this, you have theorem about weight modules that they form a ribbon category. Is the tensor unit always simple?
In this case, yes.
In this case,
yeah, this is.
So I was confused with that.
So if the tensor unit is not simple, then you will never get I guess you will never get a rigid structure. But it's very interesting. It's beyond the scope of what I.
Here always simple.
Yeah.
Okay, apart from the fact that I disagree that these are technical problems, I think they are interesting conceptual problems.
I shouldn't have said it. It's just.
I think it's and on some future programming, 5 or 10 years, we will have talks about it. I'm pretty sure.
It's more the thing you have problems that look so small that are highly influential at the end, if you can resolve them.
Okay. But anyway, let's thank Thomas again for the nice talk and for bringing up these small, innocent-looking problems.
I was doing